Okay, can you see this page?
Yes, sir.
So in the last class we were discussing the control system design objectives. So many objectives we have uh, discussed. So one of the major objective is to ensure robustness of a system that we saw, and we also discuss uh, some classical robustness measures and some modern robustness measures such as infinity norm of sensitivity and complementary sensitivity transfer function and classical measures gain margin phase margin. So, so gain margin phase margin, as I said, that already Professor Paswaropatra discussed hopefully, but I will discuss it a little bit maybe in a deeper way. Uh, and as in the last class, I was discussing that gain margin. So this is very important. It is a factor by which the loop gain. So every terminology is important. Factor is important. Loop gain is important. Okay, it is a factor by which the loop gain can be increased or decreased till the system mm, remains stable. So these points we discussed in the last class. I do not want to elaborate again. So as we saw that if you have a feedback system like this, you have a plant GS and controller CS and my nominal loop gain, suppose that is all the gains I have. So so suppose I have added a gain block here where the nominal gain is k equal to 1. Then suppose k can be increased up to k max till the system remains stable, and can be reduced up to k mean till the system remains stable. Of course, k mean I could have written here. I should write. In fact, note down. I will correct it in the when I will upload this PDF version. 0 less than k mean because this factor I am talking about is a positive factor. Okay. So this 0 less than k mean less than k less than k max. Okay. So suppose the system remains stable for k mean less than k less than k max, where the nominal value of k is equal to 1. Okay. So then the upper side gain margin is equal to k max divided by 1 because 1 is the nominal gain, and lower side gain margin is k mean divided by 1. Got it? So similarly, phase margin also we can define like this. So remember, again and again I am saying that when you define gain margin, you should not say talk about gain cost of frequency, phase cost of frequency, and so board plot. You need not to talk because it is a physical thing. You have a feedback loop, and you are increasing the gain of the feedback loop. Okay, the factor by which the loop gain can be increased till the system remains stable. It is called positive gain, positive or upper side gain margin. The factor by which the loop gain can be reduced or decreased till the system remains stable. It is called uh, uh, lower side gain margin, or I have termed this at increased side gain margin or decreased side gain margin. You can also say it as upper side gain margin, lower side gain margin. Okay. Similarly, phase margin is also now the question is what is phase margin? Phase margin is again the amount of negative or positive phase, amount of negative or positive phase that can be introduced again. Here loop is very important. Feedback loop we are considering the amount of negative or positive phase that can be introduced in the loop till the system remains stable is called phase margin. Okay. So now the question is whether positive gain margin, like the concept of gain margin, positive phase margin, negative phase margin is there, or increased side phase margin, upper phase margin, lower phase margin is there or not. That I will come slowly. So this is the concept of phase margin. So here again, everything phase margin, gain margin, all these properties we have to say with respect to a loop. Okay. amount of negative or positive phase that can be added into the loop till the system remains stable is called phase margin. So here we have shown, we have tried to show through a typical Nyquist plot. So this is the Nyquist plot or polar plot of the system. This is omega equal to 0. Here it is, as you know, this arrow indicates omega is increasing in this direction, and here is uh, omega equal to infinity. So this is your gain cost of frequency. Although I have wrongly written here, it should be omega CG, not CP. The omega, this is gain cost of frequency. That means the the loop gain, the frequency at which loop gain will be equal to 1, magnitude of the loop gain. Okay, this is a unit circle. Okay, and this is your phase cost of frequency. That is the frequency at which the phase of the loop will be minus 180 degree. Okay, that is phase cost of frequency. And suppose this is your D, so obviously this is minus 1. That means this D will be less than 1. Okay, so the factor, so here gain margin is what? Gain margin is the factor by which gain can be increased such that the loop gain will be equal to 1. 1 means it will sustain, it will start, it will start oscillating. Response will start oscillating. So here this magnitude is D. Obviously, then gain margin or positive gain margin here, positive side or upper side gain margin will be 1 by D. Okay, and here what is the lower side gain margin? You can see the lower side here what is the magnitude? Maximum magnitude is infinity. Maximum magnitude is infinity. So the lower side gain margin is 0. So that means even if you open the loop, the system will still remain stable. So that although I have not written here, here lower side GM is 0. Yes, someone was saying something. Hello? Hello? Anyone
I
was
think
saying
someone
something?
turned on their mic by mistake.
Okay, fine. So here now phase margin, as I was saying. So this is the phase margin. That means you can see the minimum amount of phase that you can insert, so that thus minimum amount of pure phase that you can insert in the loop, so that this Nyquist plot will just touch minus 1 point is phi minus phi. If you add phi amount of phase lag into the system, into the loop, feedback loop. Okay, so for example, this this is the feedback loop, k equal to 1. Okay, so now if we add a phase tester e to the power of j phi, okay, minus of j phi, then the phi amount of phase, if we insert negative phase, if we insert in a loop, then the system will remain, system will start oscillating, because this point will just it will rotate clockwise by theta angle. Okay, that means this point will touch here. Okay, so that means that the minimum amount of phase lag that is needed to make this system, the system corresponding to this Nyquist system, corresponding to the system with this Nyquist plot, will remain unstable, will become unstable, is phi. That means phase margin here, that's why it is phi. So here the question is, this is your positive phase margin or negative phase margin? So obviously this is your negative phase margin, but here, whether, no, now the question is whether positive and negative phase margin kind of thing, upper phase margin, lower phase margin kind of things exist or not. In case of phase margin, this does not exist, because the phase plot, what's called the Nyquist plot, is symmetric with respect to your x-axis. So that's why upper side phase margin, lower side phase margin doesn't matter. So that's why here simply we use the term phase margin. Here, unlike the gain margin concept, we do not use upper gain margin, upper phase margin, or lower phase margin. This is because this is symmetric. This Nyquist plot is symmetric with respect to be- because uh, because uh, because in this side also one plot will be there, right? So Nyquist plot is, I have drawn here polar plot, but if you draw the Nyquist plot, the mirror image will be there. So it is symmetric with respect to your x-axis. So that's why here, unlike gain margin, there is no positive phase margin and negative phase margin kind of thing, or upper side phase margin, lower side phase margin kind of thing. So here, just we will use the term phase margin. Okay. So some examples we will consider. Then your funda will be more clear. For example, this one, this system. Uh, just this is your loop transfer function. I have absorbed plant controller, all the things inside this this loop. Suppose ls is equal to 1 over s plus 1 whole cube. That means nominal gain here k, if you insert nominal, there is no, this is a direct path, so gain, nominal gain k is equal to 1. So now what is the gain margin of this system? We will find gain margin using root locus. You can easily see that the root locus of this system will be like this. This is real axis, imaginary axis. This is 60 degree, 60 degree. This is minus 1, and this is infinity. So, so this will be the part of root locus, and as this angle is 60 degree, this is 1. So this magnitude will be root 3. Okay, that's why plus j root 3 minus j root 3 every time. So this is a typical system for which you can draw root locus exactly and directly. Okay. So from this root locus, you can easily say that the gain corresponding to this frequency root 3 radian per second will be equal to this one. The branch, the gain at which the gain for which here here gain is equal to 0. In this direction gain will increase, and in this direction also gain will increase. So here so critical gain, or the gain at which it crosses imaginary axis, will be 1 by ls with s equal to j root 3. So it will be 8. You can easily say that here the positive side gain margin is 8. Positive side gain margin, that means your nominal gain is 1. If you increase, suppose you have added a gain block here with k equal to 1. Now if you increase the k equal to 1 2 3 4 up to dot 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 8, then what will happen? When the k equal to when the gain k equal to 8, the system will start closed loop system response. If you see output or whatever it is, if you give some reference input, say, or if you see the its impulse response, whatever it is, this response will start oscillating at k equal to 8. So that's why your upper side gain margin is 8. Now you can easily see from this figure that if you reduce the gain even to 0, it doesn't matter. System will still remain stable. So the factor by which the loop gain you can increase is 8. The factor, positive factor, of course, the positive factor by which the gain you can reduce is 0. So the lower gain margin is 0, and upper gain margin is your called the lower gain margin is 0. So lower gain margin should be as less as possible, right? Lower gain margin should be as less as possible. So lower gain margin is here 0, and upper gain margin is here 8. Okay, so that I have written 0, or you can also say it as minus infinity in terms of dB. If you write, it will be minus infinity dB. Okay. So if it is if it is infinity, then it will be plus infinity dB. Upper gain margin is plus infinity dB can be. So here upper gain margin is 20 log of 8, log 10 8. Okay. So a lower gain margin is minus 20 log of 0. Okay. So uh, that is minus infinity dB. Okay. So this is the concept of your lower gain margin and upper gain margin. Similarly, for example, this system, this system, this is an unstable system, and the root locus plot will be like this: k equal to 0, at s equal to 1, k equal to 0, and and this root locus branch will cross, will enter into the left half plane at k equal to zero point 0.5. As I said, the nominal gain k here, if you add a block k, you can add a gain here with k equal to 1. That means the system will remain intact. Now, if you increase the k, uh, uh, if you increase the k, you can easily see, if you increase the k, whatever gain it will be, it will still remain stable. That means even if you make so so if you make k arbitrarily large, it doesn't matter, the system will remain stable. So that's why here positive gain margin or upper side gain margin is infinity. Okay. And you can see, but if you reduce the gain by a factor of 2, one is the gain margin, one is the nominal gain, but if you make the gain to zero point 0.5, that means a factor of 2. If you reduce, okay, then what will happen? The system will become unstable. So here the negative, here decreased side gain margin or lower side gain margin is 0.5 divided by 1. So that is equal to minus 60. Okay. So this is one important thing. And the most important information that we must say here, that if you have, okay, can you say now from these examples, uh, when decreased side gain margin will be decreased side or lower side gain margin will be non-zero? These two examples I have considered. Can you say anyone that when the decreased side gain margin or lower side gain margin will be non-zero?
If poles
Zero
on
is the,
RHP,
yes, good. If a system has poles in the RHP side, right half plane pole, or it is an unstable system, then your lower side gain margin will be non-zero. Okay, because some minimum gain is needed in order to ensure its stability. For example, for this plant, minimum gain that is needed to make the system stable is 0.5. Okay, so that's why that means for for gain k greater than equal to zero point 0.5, the system remain stable. That means here here if you add k equal to 1, okay, so if you reduce the gain k to zero point 0.5, below zero point 0.5, then it will become unstable. So at least 0.5 is needed. Okay, so that means for unstable plants, you will have you will find some lower side gain margin also. Lower side gain margin will not be minus infinity dB. In that case, lower side infinity gain margin will be more than 0. Okay, more than 0. So that's, for example, for this one, it is minus 6 dB. Okay. So now we'll go to a we'll consider one example where we'll see, I think, some more interesting. Can you see this?
yes.
Yeah. So so here one interesting example I have considered. This is a second third order system. Again, k is here nominal gain equal to 1. No gain block is there, means here nominal gain is 1. So I have drawn root locus So root locus for this system will be like this. You can easily verify. You all know root locus. This is real axis, imaginary axis, and uh, uh, this is two poles at -2 and one at 0.5. So root locus branch will start at open loop pole and end at open loop 0. Okay. So how many zeros are there? Here 3 open loop zeros at infinity are there, right? Number of zeros at infinity. Root locus branches will start at open loop poles and close at open loop zeros. So you can ends. I should not use the term close. Ends at open loop zeros. Okay. So here k equal to 0. Here you can see k equal to 0. And ends at open loop 0. 3 open loop zeros are there. Those are at infinity. So that's why the k ends at these branches ends at for k at k equal to infinity. Okay. So the number of branches that goes to infinity is 3 because the relative degree is 3. You can easily verify that I am not again saying. You can easily verify that the here gain is equal to 2 by 3 and here gain is equal to 3. Okay, here gain is equal to 3 and here gain is equal to 2 by 3. So then you can verify that what is the lower side gain margin. Lower side gain margin is the that means the system remains stable for 2 by 3 less than k less than 3. So the lower side GM, upper side GM is 3. Upper side GM is 3 by 1, that is 3. Lower side GM is 2 by 3 by 1, that is 2 by 3. Okay, we can also see this gain margin. This is the way how to find gain margin from root locus. It is a very easy method to determine gain margin using root locus. Okay, I do not know whether this concept was given to you earlier or not, but this is a very nice idea. This gain margin, it is easy to use root locus to determine a gain margin of a feedback system. But phase margin you cannot find out root locus. Okay, for that frequency response. Yes.
So, so like yes, sir, we can also use RH criteria also, right, to determine the range of k so that the system is stable, like to find
Yeah,
the.
yeah, but Raut, yeah, Raut-Harish criteria you can also use. Okay, that is also fine. But sometimes Raut-Harish criteria may be difficult to solve. No, means those. But root locus is easy to draw. Or which one is difficult? Root locus is difficult to you to draw. Because if it is a higher order system, you have to do so many calculations in case of Raut-Harish, yeah? Hmm? Because you have to know, you have to, what you have to, anyway, yeah, there also you can do. Yeah, using Raut-Harish also you can do. What is the range of gain if you can determine, that is 0 less than Kmin less than Kmax, if you can find out. Okay, that and then you can determine. Yes, that is also possible. But to me, root locus is easy compared to the Raut-Harish. Okay. So anyway, that is up to you. Yeah.
Sir, but the value of k at g omega crossing is coming from the RH criteria only, no?
Which one?
The value of k at g omega crossing, like k is equal to 3, it comes from RH criteria. We solve it and
Yeah,
then get.
yeah, 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 yeah. Yes, yes. It is coming from value of k.
Yes,
Uh,
that thing that j omega axis crossing, that thing to apply RH criteria also,
yes,
like
yes, yes, yes. Yeah,
so
yeah,
like
yes, correct.
if
Yes,
like
yes,
by
yes.
RH criteria only we can get the entire range, then like I think it is more efficient in calculation, like.
That yeah, RH criteria you have to use to determine imaginary axis crossing. You are saying, right? To determine the image.
Yes, sir.
Yes, sir, like for root locus also we have to like ultimately use RH. So like if only by RH you can ultimately find the range, then like I think it is better.
Mm, mhm, mm. Yeah, ultimately we are dependent on Routh-Harris criteria. Yes, to determine the imaginary axis crossing. Yeah, correct. Okay. So this is about root locus. Using root locus, you can determine the gain margin, and then the basic concept is important. So for gain margin, you need not to draw board plot or something like that, right? Only to obtain gain margin. But you can use Nyquist plot also to determine gain margin. So as you can see for the same example, this example I have drawn the Nyquist plot, and and uh, and you can see here this this crossing will be at this magnitude is equal to 1 by 3, and this magnitude is equal to 3 by 2. Okay, so this is omega equal to 0, is increasing, and it is going up to this omega here, omega equal to infinity. See, again here omega equal to minus infinity, and then omega equal to 0 minus. Okay. Oh, and from 0 minus to yeah, 0 minus, there's infinity minus, and then omega equal to infinity, 0 plus to infinity. Yeah, here also you can see that the factor here it is 1 by 3, and the factor by which the loop gain you have to you have to increase, so that the system remains stable, is here it is 1 by 3. What is the factor? You have to multiply is 3. Okay, so that this point will touch this one. Similarly, the factor by which you have to reduce the gain, so that the system just remains stable, is here it is 3 by 2. If you reduce by, if you multiply a factor in the loop gain 2 by 3, then this point will just touch this minus 1 point. So that's why the upper gain margin is no, upper gain margin is 1 by a1. A1 is this distance, okay, and a2 is this distance, okay. So 1 by a1 is 3, and 1 by a2 is 2 by 3. So here you can see the phase margin is this one. So although I have not here, I have marked, but I have not calculated. But you can calculate easily uh, by determine uh, what is the magnitude here. Okay, and that you can calculate, and then you can then is gain cost of frequency you can determine, and what is the phase angle of Lg omega at gain cost of frequency you can get, and from there you can get the phase margin. Angle of Lg omega at gain cost of frequency will be this one. Okay, angle of Lg omega at gain cost of frequency, from that you will get this angle, and then this angle if you subtract that, then phase margin will be minus 180 degree plus this angle, then you will get phi. So phi equal to minus 180 degree plus angle of Lg omega at gain cost of frequency. Okay, so in that way you can get phase margin, and you can easily see this is the amount of negative phase you have to include. So what is the amount of positive phase you have to include? Amount of positive phase is this one. Since the root locus is symmetric with respect to x-axis, so amount of positive phase and amount of negative phase will be same. So that's why phase margin, there is no concept like upper side phase margin or lower side phase margin like that. Okay, phase margin is that's why it is called just simple phase margin.
Sir,
So
sir, like I had a doubt. Like in the first example, can you like show that again? That 1 by s plus 1 whole cube.
which one? Oh, this is in other. Just wait. Yeah.
Like in like you said
Yeah.
that.
Yeah. This
Yes.
one, right? Yeah.
Yes, sir. Sir, you said that like the lower side gain margin will be non-zero only like there is a pole in the right of plane, right, of the. So like if you apply RH criteria in the first case for that S plus 1 whole cube example, like I get an additional condition like K should be greater than -1. That thing, like, can you like?
No, that's why I said no. At the beginning, it is the amount of positive factor. 0 less than K mean less than 1. 0 I forgot to write. I said no. This is 0 less than is the amount of positive factor. Okay.
Okay, sir.
Here this is 0 less than K mean less than K less than K max. Got it? We certainly do not want to change this negative feedback to positive feedback. Got my point?
Yes, sir. Yes, sir. Understood, sir.
Yeah. So, this is about gain margin. Using Nyquist plot, you can determine phase margin. So, the advantage of Nyquist plot is that you can simultaneously determine gain margin and phase margin. So, the same thing I have written here. Nyquist plot is symmetric with respect to x-axis. So, that's why there is no term like positive phase margin or negative phase margin. Just simple phase margin concept to use. So now what is the limitation of gain margin phase margin concept? So as per the definition, the gain margin phase margin that gain margin, when you are saying, we are assuming that there is no variation, there is no change in the phase. Similarly, when we are defining phase margin, we are presuming that there is no change in the gain, loop gain. So that means can guarantee gain margin phase margin measures can guarantee robustness against pure gain variation or pure phase variation. But even simultaneous gain phase variation may be there. Okay, simultaneous gain phase variation is the most the very practical thing. So gain phase tester, that's why I have used. So here pure gain margin means phi equal to 0, and pure phase yes, pure gain margin means phi equal to 0, and pure phase margin means K equal to 1. Okay. This is the gain phase tester that we introduce in a feedback loop to determine gain margin and phase margin. Okay, so again I am saying, in case of gain margin, what do we do? Phi equal to 0, and in case of gain margin, we do no, in case of gain margin, we set phi equal to 0, and in case of phase margin, we set K equal to 1. Okay, gain tester and phase tester, and this is a gain phase tester. So that is the disadvantage. Pure gain variation and pure phase variation can only be guaranteed by the gain margin and phase margin norms. So now, how to take care of these things? Is there exist any better norm? That is the question. So as I said, there are two main sources of uncertainties. One is uh, uncertainty in the system parameters. Another is uncertainty due to unmodeled dynamics or neglected dynamics. In the last class, we discussed these things in detail. Okay. So now, for example, if there is system parameters variations in the system, then forget about gain margin, phase margin. What is the suitable norms that can guarantee that, well, my system is robust against parameter variations? Okay. So to introduce that, what I have done, I have drawn a simple feedback system, into feedback system. So G S comma alpha, here alpha means it is an uncertain parameter. It may be a pole location, it may be zero location, it may be a gain. Okay, so anything it can be. So the alpha is an uncertain parameter. So alpha is not fixed. So that's why I have marked it as G S comma alpha separately. So now we will first define that S alpha G. S alpha G, we are defining like that sensitivity of G sensitivity transfer function we will use. So sensitivity concept G. So GS comma alpha is your plant, uncertain plant, where parameters are not fixed, or some parameters, one parameter at least, is uncertain, or uh, some upper limit or lower limit of the parameter is known. So S alpha G, what we are doing, S alpha G we are defining as sensitivity of G, this plant, with respect to alpha. So, so what is the definition? Definition is hmm, limit alpha tends to 0, del G by G divided by del alpha by alpha. So that we are defining as S alpha G. Okay. So S alpha G we are defining like that. The sensitivity of G with respect to alpha, that is equal to limit delta alpha tends to 0 del G by G. That means if there is any percentage change of alpha, what is the meaning of this? If there is any percentage change in the parameter alpha, then what is the percentage change of the, the plant transfer function? If there is any, this is percentage change in alpha, this is percentage change in G. So the ratio is called sensitivity function when alpha tends to 0. So this you can, so as per the definition, so as per this definition you can write it like this: del G by G and del alpha by alpha, because alpha tends to, as alpha tends to 0. So this is known as open loop sensitivity, because because we are here only considering plant sensitivity of plant G with respect to alpha. Okay, so this is open loop sensitivity. And now, so open loop sensitivity S alpha G is equal to del G by G, the percentage change in G divided by percentage change in the parameter alpha. Similarly, the sensitivity of the closed loop transfer function. So if you close the loop with a controller, then suppose the closed loop transfer function is your GC by 1 plus GC. Of course, G of alpha C I have not written for convenience. Okay, the closed loop transfer function will be GC by 1 plus GC, and then ultimately you will get sensitivity, closed loop sensitivity. So this is your open loop sensitivity S alpha G, and S alpha T is your closed loop sensitivity. This is equal to del T by T divided by del alpha by alpha. So now you can easily see that you can derive. I have not derived, so you just derive it. Is very one or two line is needed more thing. Just differentiation you have to do, because T is given. So you have to write what is del T by T in terms of del G by G. So if you write that, then you can easily see that S alpha T is equal to 1 by 1 plus GC into S alpha G. Got it? You can easily verify that. So that's why I've written try. It is very simple. Okay. So 1 by 1 plus GC into S alpha. So you can, from this you can easily see that closed loop sensitivity is equal to sense S into open loop sensitivity. This S is very important. This is called 1 by 1 plus GC. So where G is the nominal plant. Okay. With alpha value, alpha of nominal, alpha is nominal, alpha alpha nominal value of alpha. So this is called sensitivity function. Okay, we will define. So this terminology we will use frequently now onwards. This sensitivity function. The sensitivity function is equal to what? 1 by 1 plus GC, and you can easily see that closed loop sensitivity equal to sensitivity function into open loop sensitivity. So open loop sensitivity, one plant is given means open loop sensitivity is fixed. Okay. So now what is the use of feedback then? Using feedback, you can, even if this may be high, you can make this one low by lowering down S. Okay, if you can make S as low as possible, then the closed loop sensitivity you can reduce. Okay, so closed loop sensitivity you can reduce, and so the objective of robustness against, so you can make a feedback system robust against parameter variation if you can make this S, if you can design controller C such that this S is as less as possible. Got it? S is as less as possible. So this S you can also write like that, 1 by 1 plus L. What is L? L is your loop transfer function. As I said, always this terminology I'll use, loop transfer function. Everywhere you draw, if you use Nyquist plot is drawn for loop transfer function, loop locus drawn for loop transfer function. All are loop locus of a transfer function does not have any meaning. Similarly, Nyquist plot of a transfer function does not have any meaning. Nyquist plot of the loop transfer function, we must say, because the Nyquist plot we draw to determine if the feedback loop is closed, then the system will remain stable or not. Similarly, loop locus is drawn given a given a no, given an open loop or loop transfer function. If the feedback is closed, then the system will remain stable or not. So that's why loop transfer function is very important. We always should say the loop Nyquist plot of a loop transfer function, loop locus of a loop transfer function, so and so. Bode plot of a loop transfer function. Okay. So as I said that if you want to have a good robustness against parameter variation, then what you should have, S should be as less as possible. So S should be as less as possible means what? From this expression, you can easily say that L should be as high as possible. If L is high, then only S will be small. Okay. So high gain. So 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 now L should be as high as possible. Now with this, now we will see what is S, how to represent S. What is the physical meaning of S? Okay, in terms of transfer function, we saw that S equal to 1 over 1 plus L. Now, if you represent this L S in terms of Nyquist plot in Nyquist plane or polar, what's called loop L j omega plane, if you want to plot S, then how it will means how will you represent this? What is the physical meaning of S in respect of Nyquist plot, or what is there in S? What is there in S which is helping us to achieve robustness against parameter variation? Of course, we can see from this expression that so S is a multiplying factor here. So as naturally as S becomes low, your open closed loop sensitivity becomes less. That means if there is any parameter variation in the open loop plan, that will affect least in the less in the if you close the loop. That's why we use feedback amplifier. Okay, because the temperature sensitivity, change in temperature will affect least, because feedback action in an amplifier reduces the sensitivity. This is the concept. Actually, that this concept is coming from the feedback amplifier. Okay, the sensitivity term. So now we'll see how to represent S in Nyquist plane. So S j omega, as I said, S j omega you can write like this, 1 over 1 plus L j omega. And then from here you can see that what is S j omega inverse. S j omega inverse is 1 plus L j omega. Now you can see that if you want to draw your what is S j omega inverse. Now you see. So I have drawn it in a loop L j omega plane. Nyquist plot is drawn on L j omega plane, no, because it is for loop transfer function. So this is a real axis, this is an imaginary axis, real of L j omega, imaginary of L j omega. So this is your L j omega plot. This plot is your L j omega that you know, the typical L j omega. Now what is 1 plus L j omega? Then if this is your L j omega at any frequency, say omega 1, what is my L j omega? So this so 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 this is my L j omega plot. So this is your 1, this is here to here is my mod of L j omega, L j omega 1. So this is 1 plus L j omega. Okay, so this is my L j omega, this is 1 plus L j omega will give you 1 plus L j omega. So what is 1 plus L j omega? This is your, here this distance to this distance will give you 1 plus L j omega, and this is your vector 1 plus L j omega. Okay, so this is your L j omega vector, this is your 1 plus L j omega vector will give you 1 plus L j omega vector. Vector sum of these two is equal to this one. Okay, this is 1 plus L j omega. So you can easily see that S j omega inverse is what? The distance of the Nyquist plot from -1 point. S j omega inverse physical meaning of, what is the physical meaning of S j omega with respect to Nyquist in Nyquist plane, or you can say in L j omega plane. S j omega inverse is the distance of Nyquist plot from -1 point. That I have written here. S j omega inverse is the distance of Nyquist plot from -1 point. Now naturally we are interested in, so S j omega now this distance is of course frequency dependent, right? This distance for 1 omega, this one distance you will get, for another omega another distance you will get. So we are interested in the minimum distance. So because so which one is good? This Nyquist plot should be for robustness. Your Nyquist plot should be as far as away from -1. As far as from that means it should be as much as away from the -1 point. Got it? Because if it is far away from the -1 point, even if there is perturbation, it will not touch -1 point. That means system will not remain, will not become unstable. So controller design, one of the controller design, when you will design controller, we should keep that point in mind. Your Nyquist plot of loop transfer function should be much away from a -1 point. So which were, so as S j omega is dependent on omega, we are interested in the minimum distance, minimum value of 1 plus L, right? Minimum distance. So minimum distance, minimum of 1 plus L j omega, that I have marked here. Minimum of 1 plus L j omega is equal to S inverse. Okay, so we will define first ms as like this, max of omega S j omega. So ms inverse is 1 by max of omega S j omega. So then ms inverse you can also write as mean of 1 plus L j omega omega. So ms inverse is then what? Ms inverse you can say, or S j omega mod inverse. No, this is equal to S j omega mod inverse. So this we are terming it as ms inverse, where ms is like this. Okay, It is also called infinity norm. Because it is the infinity norm here. Simply we are defining like that. Infinity norm of a transfer function is equal to max of omega s j omega. Of course, we are assuming it is a scalar transfer function. If it is a multi-input, multi-output system, then the definition is a little bit different. That I am not going into that. So what is the infinity norm then? This is the infinity norm is equal to this. So that is the peak value of the Bode. This is nothing but peak value of the Bode magnitude plot of Sj omega, right? That is the infinity norm. So MS inverse is the minimum distance of the Nyquist plot from Lj omega point. As I was saying, that the minimum distance is important. So for a good minimum distance, how will you draw a minimum distance from Nyquist plot? Just you will draw a circle such that this circle with center -1, such that this circle just touches this Nyquist plot. So this distance is your sensitivity inverse. That means MS inverse. Okay, MS inverse. So that means this distance should be for your robust stability against parameter variations. This distance should be as much as possible. This distance should be as much as possible means MS should be as less as possible, right? So that I have written. So MS should be as small as possible for robust stability. So in this way, so now the question is whether well, MS should be as less as possible by but to what extent we can reduce practically. Okay, so practically you can easily see that S equal to 1 over 1 plus L, but for all system, most of the physical systems are of low pass behavior. That means relative degree greater than 0, right? Most of the physical systems are of low pass behavior. So LGM, even if you choose controller to be biproper, controller to be bicasual, okay, so LS will be strictly proper. That is low pass behavior. So that's why, as it is strictly proper, at high frequency LG omega is very small because of roll off rate, high frequency roll off rate. Okay, high frequency roll off. At high frequency LG omega is very small. So that's why at high frequency, whatever controller you employ, it doesn't matter. SG omega will be very near to 1. Okay, at high frequency you cannot avoid. SG omega will be 1 at high frequency. So that is the limitation. So SG omega you cannot reduce arbitrarily. SG omega you cannot reduce beyond below 1. That's the constraint. Okay, so fortunately these parameter variations are of low frequency type. Okay, so that's why, but at low frequency this high SG omega 1 occurs only at high frequency, but at low frequency SG omega is small. So we using by employing a controller we can take care of parameter uncertainty. So MS so for guaranteeing parameter uncertainties, robustness against parameter uncertainties, your MS inverse should be as large as possible, or you should design a controller such that MS should be as small as possible. As small as possible means close to 1 you should try to keep, because below 1 it is not possible. Got it? But for example, MS, there are some limitations of this achievable sensitivity norm in case of non-minimum phase and unstable plant. If you have an unstable plant with zero location at say S equal to Z and pole location at S equal to P, then you can verify that this kind of relation is there. That I am not proving the difficult relation using interpolation theory, or all those things are needed. MS is always greater than equal to 1. Okay, so that's why unstable and non-minimum phase plants are difficult to control because sensitivity you cannot make. You can never make close to 1. It is always greater than equal to 1 if there is. You can see if the pole and zero locations are close to each other, then this ms value will be very high and it will be difficult to control. That's why you will see later that this in our laboratory inverted pendulum system and all these things, they are non-minimum phase systems with non-minimum phase zero, unstable and non-minimum phase zero. That's why they are difficult to control. Okay.
Sir,
So yes,
sir, we have class at 12 o'clock. Can we please leave?
yes. I have completed. So today I'll stop it. So up to sensitivity I have finished. So do you have any doubt? Those who are having class, they may leave, but those who are if you have any doubt, you can ask me.
Sir,
Yes.
so like just a request, sir, like can you also tell us like with respect to any book, which chapters we can refer for covering the topic that will be discussed in the class, like with respect to a particular lecture that we will be
See,
discussing.
yes, that I am understanding, but as I said, I am not following any particular book. For 5-6 books I have followed. Also, I have 10 years, more than around 10 years experience in this field. Okay, so I am also applying my concept, and mostly I am following, as I said, Ulovich, W.A. Ulovich book for whatever I have taught. Ulovich book, W.A. Ulovich. Okay, control system analysis and design by W.A. Ulovich. Okay, that some most of the things you will get in that book. Okay, I will follow for this part mostly Ulovich book. Okay, Ulovich books, loop goals is there. Loop goals. There is a chapter named loop goals. Okay, so this loop goals I am teaching now. Okay, but many things you will not get, which is whatever concept I am having so far, whatever experience I am having. Based on that also I'm trying to say, because in Ulovich book also this is there, but in the appendix, this relation, for example, you will not get there in that chapter, but this is there in the appendix. Okay, from there I have taken this concept. So also not these things may not be available in that book in that much details. Okay, for example, this gain margin concept and all these things in Ulovich book also, this negative phase, what's called positive upper side gain margin, lower side gain margin concept in Ulovich book is also not there. They have said just simply gain margin, but that I have followed from some papers, technical automatic control papers. So there I can say those things. But from that, from those papers, I am teaching automatic control papers. This gain margin and phase margin, this gain phase tester, this concept, all these things I have taken from from those journal papers. Okay. So my suggestion is that you study the Ulovich book as well as my notes. You try to attend the classes. If you face any doubt, you can ask our TS. You can if they fail to explain you, if you are not satisfied, you can contact me. I'm always there, no problem. Okay. So any other things you want to ask? If you have any question. Do you have any other question? Hello? Any other question? Okay, thank you.
So can you please upload the PDFs of the notes?
Yeah, a PDF I will upload after tomorrow's class. Okay.
Okay, sir.